Check it out now, y'all.
NanoHub U, online instruction.
Hi again. We're back, and we're going to build on the discussion of the previous lecture. And in this lecture, we're going to go from a Fourier series, which contains an infinite number of sines and cosines to represent some periodic function f of x. We're going to extend that idea to a Fourier integral, where we're going to require an infinite number of terms now to represent some function f of x. So again, just a quick review. The Fourier series is very useful if you have a periodic function. The periodicity of this function is specified by the parameter capital sub L. And in this very simple case, we've got a sequence of pulses. The pulse width is the parameter L, is designated by the parameter L sub P. So the question we're going to ask, and we're going to answer it in this question, is what happens if the spacing, the periodicity capital L, gets very large? So in other words, what happens if the spacing between these pulses increases, and we're very interested in the limit when there's only just one pulse, right? So if L goes to infinity, capital L goes to infinity, there's just going to be one pulse at the located at the origin of the coordinate system here. What do we do? What are the implications for this Fourier series? Well, the implications are that we need more and more terms progressively. We'll need more and more terms in this Fourier series to represent this to represent this function as the periodicity of this wave function increases. And in the limit, when capital L goes to infinity and there's only one pulse localized at a particular point in space, right? We're going to need the continuous distributions of sines and cosines. So the concept of periodicity for this one pulsed function, that concept kind of goes away, and as a result, we don't need a finite number of sines and cosines. We actually need an infinite number of them. So the mathematics to describe that situation is sketched out in this slide. And what it basically says is, that if you give me some function f of x, which in the case we're going to consider is going to be a single pulse of width L sub p, right? That function f of x can be represented by sines and cosines. The sines and cosines are represented by this exponential e to the I kx, okay? And the coefficients that multiply the sines and cosines are now in turn going to be a continuous function g of k, which we in principle don't know. So what we're going to have to do is we're going to have to devise a formalism to calculate these g's of k's that are appropriate to multiply each exponential term e to the I kx, so as to reproduce the known function f of x. So when you look at an equation like this, I guess the first thing you have to do is not panic. You have to be able to systematically dissect what the equation is trying to tell you, and that's basically the purpose of this lecture, is to discuss this Fourier integral and provide you with some insight into what it's actually doing. The physical application of this Fourier integral is we're going to use it to represent wave packets, which are going to be localized wave functions in space. And these localized wave functions in space are then going to be used to represent free particles that are moving either to the left or to the right. So that'll come in the next lecture. But right now we have to work a little bit on the mathematics behind this Fourier integral. In principle, we have to devise a way to calculate these coefficients g of k that multiply the e to the I kx factor, and this function g of k that can be put in here can actually be determined by the known function f of x integrated over all space times e to the minus I k x. Okay, so in this case, the k prime is used. It's a dummy variable, right? You tell me what k prime is. If you give me the function f of x, then I can perform this integral and I can get this function g of k prime. I can then put this function g of k prime back into here, and I've got an identity, right? So it's very similar to a Fourier series, but now the coefficients that multiply the various sines and cosines, those coefficients are not discrete. They're described by a continuous function, this function called g of k. Now, there are a number of things that you have to recognize with this formula, and I try to list those points in this slide, which you can read on your own. But ultimately, what you have to realize is you know what f of x is. You specify f of x, and for the known function f of x, you can always find out what the coefficients are in the Fourier integral by evaluating this particular integral right here. This evaluation requires you to pick a specific value for k prime, right? So you must specify a value for k prime, and when you do that, after this integral is evaluated, then you have the value of this function g at that particular value of k prime. Notice that because we've got a complex number here for the sines and the cosines, in general, g of k prime is going to be complex. So there's going to be a real and an imaginary part, right? The integral is kind of an ideal integral, right? Because we're going to have to do an integral from minus infinity to infinity. That's what this equation says. And very often, we're not asked to do those integrals over minus infinity to infinity. So that sometimes causes concern, but in many cases you can work this out in a pretty straightforward way. So that integral shouldn't cause you to just close the book and walk away. The other thing I'll say is that this expression here basically requires you to specify an infinite number of different k primes, right? So in order to pull this integral off, you need to know g of k prime for every k prime you can imagine. And so there's an infinite number of k primes. For each k prime, you're going to have to do an integral from minus infinity to infinity. So I like to refer to this as almost like a problem that has two infinities associated with it. And that also causes difficulty, right? You have to know how to deal with that. Sometimes this integration works out so that you get an analytical expression for g of k prime. And for the case that we're considering here, that's going to be the case. And that's a special situation. And when you have those special situations, you can then write down a closed form function for g of k prime. And that's really very nice. So I think those are the important things that you have to remember when you look at this integral. The important thing is not to panic, but to try to understand what in fact this Fourier integral is doing. And to try to illustrate that case a little bit more clearly, I like to just briefly discuss what this Fourier transform integral is doing, and I like to frame that discussion in terms of this function f of x, which is a single pulse, right? It's got an amplitude a, and it persists for a distance L sub p. Everywhere else along the x-axis, this function is equal to 0. So what we're going to need to do is we're going to need to plot this factor e to the ik prime times x, okay? And to do that, we're going to pick a particular value of k0 prime. I don't care what it is, right? But that particular value of k0 prime allows us to then write this integral this function in terms of a cosine function and in terms of a sine function, which is imaginary because it's got the I in it according to Euler's theorem. And that allows us to make plots of cosine of k0 prime x as a function of x, and also minus I sine of k0 prime x as a function of x. And we can put these plots and line them up with the plot of our function f of x such that the origin of x equal to 0 is all lined up, okay? Now what this Fourier integral is telling us to do is it's telling us to multiply our function f of x by either the cosine of k0 prime x, the k0 prime is the parameter that we chose, right? When we multiply those two things together, what we get is we get 0 everywhere outside the region of the pulse width L sub p, and that's because f of x is equal to 0 out here, and it's also equal to 0 out here. So when we do that multiplication, we get 0, and then in the middle, where the pulse is non-zero, right, we just get the individual factor cosine of k0 prime x plotted over the width of the pulse. In this case, the width of the pulse is L sub p. And what this integral is what this formula is telling us to do is it's telling us to integrate that product of f of x times the cosine of k0 prime x over all x from minus infinity to infinity. And that just basically means sum up the area under the curve. So what I've done here is I've plotted the area under the curve in blue. And what we have to do is we have to figure out what the net area is enclosed by that blue curve over the region from 0 to L by L sub p. So because it's a sine wave of constant amplitude, what you can see very quickly is this part of the curve exactly cancels that part of the curve, right? This part of the curve for the particular value of k0 prime that I picked, this value is slightly more negative than this region of the curve, and so when I add this to this, I'm going to get a negative value, and that just simply means that my function g of k prime for the particular value of k0 prime that I picked, I'm going to have some negative number associated with this integral. And that negative number is going to just basically relate to the area of the curve here compared to the area of the curve here, since these two areas are precisely equal but opposite sign polarity. I can do the same thing for the imaginary contribution to this integral, right? The imaginary contribution involves the sine of k0 prime times x. Of course, the sine of k0 prime starts at x equal to 0 and oscillates like I've got drawn. The solid curve indicates the area that I get when I multiply my function f of x times the sine of k0 prime over the region from 0 to L sub p. Outside of that region, again, the integral is equal to 0 because my function f of x is equal to 0. And what I then have to do is I have to sum up the area under this curve, and I can, qualitatively make the same argument. This area here, which is negative, will cancel that area there, which is positive. Here I've got slightly positive area, which is greater than the negative area enclosed here. When I add this to this, I get a positive number. I got to remember the minus sign in my integral. So that means that ultimately the value of g of k prime at k prime equals to k0 is going to be some negative value that I just indicate schematically on this plot. So what you have to do to evaluate these Fourier integrals is you have to basically do this type of analysis for every possible value of k prime, right? And if you do that, then maybe you would get some sort of a curve that looked like this. For the imaginary part, you would get some other curve that happens to look like this for the real part. These dashed lines are just schematic to indicate to you the different values of k prime could produce either positive or negative values for the real or imaginary part of that Fourier integral. So graphically, that's what the Fourier integral is actually doing. Of course, the trick is to evaluate that integral analytically, and for the case of this single pulse, right, of width L sub p, it turns out you can do that evaluation analytically. And of course, this was one of the homework problems that was given in the first homework set. So if you didn't understand how to do that first homework problem, let's make sure we all understand how to do it here. So here I just work out the math. I calculate what the g of k prime is for this f of x, which specifies this single pulse of width L sub p. You can see what happens immediately is the integral goes from an integral from minus infinity to plus infinity to an integral that I can handle. It just goes from 0 to L sub p, and I just have to evaluate this integral over the range of the pulse width. You can check through the arithmetic. At the end of the day, I make a few substitutions to make the final result mathematically appealing. At the end of the day, you find out that the g of k primes that are required to reproduce that pulse of width L sub p, just one pulse now, is given by this sine x over x type function, where x is equal to this wave vector k prime. L sub p is the pulse width divided by 2, right? So you tell me what k prime is, and I can put it into this formula, and that tells me the coefficients g of k prime that I need in order to represent that single pulsed function f of x. The important point to recognize here is that there's no restrictions on k in this problem, right? So unlike the case of a periodic function that repeated itself periodically with position, for this particular problem, which has no repeat distance, it's just a single pulse, there's now no restrictions on this wave vector k. We can calculate the magnitude. So if you look at this detailed expression for g, right, it's got a real part and an imaginary part because it's got this e to the minus I function, right? So that means I can always rewrite this explicitly in terms of a real part and an imaginary part. And once I have the real and imaginary parts, I can always calculate the magnitude by multiplying g of k star times g of k, and when I do that, I get an expression that looks like this. So this represents the magnitude of the g sub k's, and I can then do a plot, right, of the magnitude of g sub k as a function of k. And what I find is that basically all the k values that contribute to this Fourier integral are localized between the values of minus pi and pi, where my dependent variable is k times the pulse width L sub p divided by 2. So this is an example of a very specific but very relevant problem. It's a pulse that's localized in a given region in space. And what we find from this analysis is that there's continuous distributions of k's that are required in order to fit that pulse. But by and large, most of the k values tend to be localized between two regions, minus pi, between the region minus pi to pi in k space. So it's important for you to understand the arithmetic behind this analysis. We are going to use it repeatedly throughout the semester, and we're also going to use it to describe something called a wave packet, which is going to describe how a free particle can be localized in space. I also mentioned that if you want to practice with this type of arithmetic, there's a very nice website which I list on this slide. If you go to this website, you can actually specify periodic pulses, right? And you can specify the distance between these periodic pulses. And this website then calculates for you the distribution of K values that are required for you to produce this particular train of pulses. And it also provides you with a visualization of what's going on, because it allows you to see the individual terms in the Fourier series. You can see how those individual terms add up. All these terms in here cancel in order to give you this zero value for the function. But every repeat distance, capital L, the sines and cosines add up in phase to give you the actual shape of the pulse that you specify. So this website is very useful. We're going to use it extensively in the next lecture, and it allows you to visualize a lot of the arithmetic that we've just worked through in this lecture. So the next thing we're going to do is we're going to describe a wave packet. We're going to discuss how you can create a wave packet that's appropriate solution to Schrödinger's equation. This wave packet is going to describe a localized wave function that is a better approximation to a free particle as it moves through space. So we'll see you when you have time to listen to that next lecture. Thank you much.